So far, we've covered two reactions to add water across a carbon-carbon double or triple bond. We've looked at the acid-catalyzed hydration in Chapter 12, and that proceeds through carbocation intermediate. Then in the last screencast, we learned about the oxymercuration reduction, which proceeds through that cyclic mercuriinium ion intermediate, and that avoids the carbocation rearrangement. Now, both of these reactions add water in a Markovnikov fashion, where the carbon atom that gains the OH is the one that's better able to stabilize the positive charge, which we also know means it's more highly substituted. Neither of these reactions is stereospecific, and so in each case, you get a mixture of stereoisomers. Now, we're going to look at a third way to add an alcohol functional group. This is a hydroboration oxidation, and we add water across that nonpolar pi bond, that double bond. And this is two examples of it, right? So you can see the example here. Notice the regiochemistry in this reaction, okay? When we look at the regiochemistry, sorry, I paused there because I forgot. I skipped something that I wanted to tell you. I want you to notice this H2O2 first before we look at regiochemistry. So when we do this BH3 here, this is the hydroboration part, right? And then this H2O2 here, that's hydrogen peroxide. And so the product there is oxidized. So the product is oxidized by the hydrogen peroxide, okay? So we have the hydroboration and then the oxidation. Now let's come over here and look at the regiochemistry of the product. I wanted to talk about reactants before products. Notice here that the OH is favored at the alkene carbon that's the least stabilized, that can least stabilize a positive charge. That's that primary carbon. And so this exhibits that anti-Markovnikov's regiochemistry. And so we say that this then goes through an anti-Markovnikov's addition. Notice here that this reaction is stereospecific, right? So in both of these, like for example, when we look at this, both the H and the OH group add to the same face of the alkane plane, okay? And so what that means then is that the alkane undergoes the syn addition of the H and the OH. Okay, so it's going to add from the same plane. I'm going to digress for just a little bit. I want to talk to you about heptane 1-ol that's being synthesized here. So if you're curious as to like why we would be interested in synthesizing this, product here is used in cardiac electrophysiology. And that just deals with the understanding the electrical activities of the heart. And so what heptane 1-ol does is it uncouples the gap junctions, which are these densely packed protein channels that allow for the cells to contract in unison. So if you're interested in cardiac surgery or really any type of pre-med or medical issues that deal with the heart, this is a chemical that's used for that. Now, in the hydroboration of an alkene, borane, which is BH3 here, so right, effectively adds across the carbon-carbon double bond. The hydrogen adds to one carbon and the BH2 adds to the other carbon. So that's the reactive species. in this hydroboration of an alkene. But unfortunately, BH3 is highly unstable because that central boron atom doesn't have an octet. Okay, so what this means then is BH3 can't be isolated. Instead, in its pure form, it exists as a gaseous dimer. Dimer, di just means two, so it's two molecules here. This is diborane, which is B2H6, and two of these hydrogen atoms here constitute a bridge between the boron atoms. Now, those hydrogen atoms are involved in what's called a three center, two electron bonds. So it's written right here for you, 3 center, 2 electron bond, and that just works to stabilize the boron atoms. Now, although those bonds provide some stability, B2H6 is very reactive. It's also toxic and explosive. Okay, so it's real hard to work with. But a more stable version of BH3 is sold commercially as a 1-to-1 complex with tetrahydrofuran. Now, this is indicated as BH3THF, and it forms this complex shown here. And the THF here acts as a Lewis base to give the boron atom its octet. You can also have a 1-to-1 complex that'll work like this, BH3 to dimethyl sulfide, which would look like CH3SCH3 or BH3DMS, okay? And these can all be used as a source of borane to do this reaction. So make sure you can recognize this. Now, when we talk about the hydroboration reaction, it's generally driven by the flow of electrons from electron rich to electron poor, so things that we've seen before. I'm going to look here at I'm going to show a ring. I'm going to try to show it flattened for you where that kind of part goes out here, and that's going to be a double bond. Okay. And then we have our borane here. Now, borane is electron poor, and we know the double bond is electron rich. So we're going to go from electron rich to electron poor. So it's going to come up here. Again, this is a concerted reaction, and this is a hydride reaction where these electrons, so you start your arrow from the center here, goes down and attacks here. And I left out a molecule of part of this, CH3. Okay. Now, when that occurs, right, in this concerted fashion, what happens right, is that we've got CH3 here, and then these two things, we've got BH2 that adds here and a hydrogen that adds here. And those add on the same side, so that's a syn addition. So the hydrogen and the BH2 add in a syn fashion. Now, the hydrogen adds to the carbon with the greater number of alkyl groups, right? Whereas the BH2 adds to the carbon with the lesser number of alkyl groups. Okay, so both of these properties can be explained by the concerted nature of hydroboration. The syn addition of that H and BH2 is an outcome of the carbon-hydrogen and the carbon-BH2 bonds forming simultaneously at the same face of that carbon-carbon double bond. And there's no charged intermediates that are formed here, so charge stability doesn't provide as much of a driving force as it does in other reactions we've seen. And so consequently, steric hindrance plays a bigger part. So let's talk about steric hindrance for just a second. When BH3 adds to an alkane, steric repulsion directs the larger group. So steric repulsion directs the larger group BH2 to the carbon atom with the lesser number of alkyl groups. Okay, because there's more room there. That's it. This is really, really nice. It shows the steric repulsion here. This is showing the steric repulsion that would occur if BH2 were to add to the more substituted alkene carbon, and that's just not going to happen, right? That's too much steric hindrance. So it's much easier or more favorable for the hydrogen to add here and the BH2 to add here. Now, even though no formal charge appears, charge stability is also a really minor factor in the regioselectivity of hydroboration. When we look at the transition states that kind of are shown here, with this particular transition state, this carbon here has a partial positive and this has a partial negative. So it also makes sense that the BH2 would add over here, whereas the hydride's going to add over here. Okay, so it's a really minor issue. Steric hindrance tends to be the more major issue. Now, the product of the hydroboration, if you notice, we haven't added an alcohol yet, right? So we're not done with this reaction. So the product of the hydroboration of an alkyl borane, right, is shown here. So this is sort of what I tried to show on the previous page, but this is showed in dashes and wedges where these two are coming out here. Now, this alkyl borane has two borane hydrogen bonds that are remaining. And one of these bonds can react with the additional unreacted alkene, okay, and add across the double bond again. Now, I want you to understand what they've done here because this always throws everybody off. They've taken this molecule right here and said that's an R group, okay? And so to shorten this, they show this as an R group here, okay? If you were to do this, you need to draw out the R group. Okay, so if you have to do this on a mechanism, test on a mechanism, you need to draw out the R group. You'll also do this in class. So where this R is here, this molecule is attached to the boron, right here, okay? And so this can then go through another syn addition, okay? Now, this dialkyl borane product still has a boron hydrogen bond, and so it's still reactive. So again, this now is R2BH, right? And so we can add that across, and then what we have is boron with three of these exact same groups attached to that boron. Okay, so three big groups attached to that boron. Each one of these is a syn addition, and the bulkier boron containing portion adds preferentially to the less sterically hindered alkene carbon atom. Now, once the trialkyl borane is formed, then it's treated with a basic solution of hydrogen peroxide, which it converts to that alcohol. And we talked about that in section 13.6. Now, when we look at this, this is showing what happens, sorry, there's a pause there. And so I've restarted, you haven't missed anything. So this is showing that after an alkene has undergone hydroboration, treatment with a basic solution of H2O2 is what produces that alcohol. And so you can see the alcohol here. Notice some features of this particular oxidation. Each of the carbon boron bonds is replaced by a carbon OH. Okay, so we end up with, because we had 3 of these attached, boom, 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 we end up with a 3 here, right? So 3 equivalents of this are produced. And the configuration at each carbon atom remains unchanged. So if it's a dash or wedge here, it's going to be a dash or wedge here, okay? Now, let's look at the mechanism with the hydrogen peroxide. So when we look at this mechanism with the hydrogen peroxide, okay, a hydrogen there, and a CH3 there. And the very first step here is a coordination reaction. And with the H2O2, what you're going to see right is we've got a hydroperoxide ion. So this right here is a hydroperoxide ion. And this, because this occurs under basic conditions, it goes through a general, hydrogen peroxide goes through a general acid-base reaction where the hydrogen peroxide becomes deprotonated to have the hydroperoxide ion. The mechanism begins with the coordination of this hydroperoxide ion to the electron deficient boron atom. So again, boron here is lacking an octet, it's electron deficient. This hydroperoxide ion's got a negative charge on it, so that leads us to believe it's electron rich. So we're going from electron rich to electron deficient here. So we get that kind of first coordination attack. Okay, now, so let's go ahead and draw the product there. And I'm going to use and follow those arrows. So if there's not an arrow drawn to it, I'm not changing it. Okay, so this is a borate ester, and I'm sorry, this is not a borate ester. We're going to make a borate ester. So what we're going to do here is we're going to see a 1,2 alkyl shift. And so when we see this shift, what happens here is that these electrons, oh, and boron's got a negative charge now. These electrons come here and attack the oxygen, okay? And then it bumps off this OH here. Now, when that occurs, now we have a borate ester. Right, which looks like this, okay? You end up repeating this step several more times, right, to get rid of all the R's. So instead of showing that, I'm just going to say here, right, repeat 2 times, okay? to change these R's over. And so what we end up with then, when we repeat that 2 times, right, is this trialkyl borate ester. Okay, so now we're going to go through a coordination reaction again, but we're in a basic solution. So what happens are that these electrons come down here and just coordinate with that boron. Now, when that happens, this is the complex that we get. Okay. Now, at this stage, it's going to go through heterolysis, and there's a negative charge. Anytime there's 4 things bonded to boron, there's a negative charge there. And I'm terrible and I keep forgetting that. So when that happens, right, these electrons here go back up on that oxygen, and that bond just breaks. And so what we now have is that deprotonated alcohol. We also have left this boron, OH, OR, OR complex here, and now that can go through this process again to get rid of, to replace this with the OHs. Now, so let's just focus on the other product at this moment. We've got a negative charge there, so it's going to go through a proton transfer reaction. We have water running around because we had OH, right, before. So what's going to happen here is that this is going to come and grab that proton, and those electrons are going to go back on that oxygen to form OH minus again. We're in a basic solution, so this makes sense. That's always really important. And whoo, now we finally have our alcohol product. So this is the mechanism that we see, right, from the borane to the alcohol product here. Now, let's do a sample problem. So consider the following reaction, which for whatever reason I did not put on your thing. And then you're going to draw the first step of the hydroboration oxidation mechanism, and then draw the trialkyl borane product, right? And then you're going to draw the product that's formed from the oxidation step. All right, so if there was a pause there, I was looking up to see what this reaction was. Mostly because I need to know to see what the reactants are before we work through this. So hold what you have. Here are the reactants, right? And BH3 THF. So that's that BH. That's that boron complex again. And then hydrogen peroxide, sodium hydroxide, this is basic, and water. Okay, so all right, we've got our problem here. We've recalibrated. So consider the following reaction. Draw the first step of the hydroboration mechanism, and then draw the trialkyl product, and then draw the product that's formed from the oxidation step. So let's kind of ask ourselves some questions here. So when we look at this, we say, what is going to be the preferred orientation of the boron? So when I redraw this, right here, okay, two cyclohexane rings, okay, and we have our bond here. The preferred orientation is going to be this way because of steric hindrance, right? There are more things kind of sticking out here. There's a lot of bulk here, so it makes sense that the boron would go here, and then the hydride would go here. Okay. The next question you need to ask yourself is, in the hydroboration reaction, what species is electron rich and what is electron poor? Double bonds are electron rich. Boron, because it lacks an octet, is electron poor. We draw arrows from electron rich to electron poor. And so when we do this, right, we draw to here, and then we start our arrow here, and it goes there, okay? And now, one, two, three, four, five. Okay, there we go. So I'm sorry, I had to count my carbons there just to make sure. All right, so now at this step, we need to remember, right, that these guys add on the same side there, okay? So it's a syn addition. So we're gonna have H and BH2. If you're asking yourself, Dr. Pierce, I like using those dashes a lot more than I like using these wedges. Well, use your dash, it forms the other one too, right? So it's gonna form both of those. So then you need to ask yourself, in the alkyl borane that's produced, how many BH bonds are there, right? And so when we produce this alkane, we have 2 BH bonds that remain. So to form the triborane, each BH has to be replaced by that R group, right? The BR. And so when we look at this, right, that means this is going to go through that mechanism 2 more times, okay, and we are going to end up with and then 2 R groups, and of course the enantiomer. And then in the oxidation step, what group replaces each boron-containing group that's attached to the carbon? And then what's the stereochemistry at this step? So this would be what you would rationalize through really for a predict the product type reaction. Okay, and so when we do this, we know that the boron there is replaced by that alcohol functional group. And there we go. There's our product. And the enantiomer, right? And the enantiomers would just be the dashes. So I apologize that this was a little rough and I left out the reactants there and had to pause the screencast. If the burning question in your heart is, Dr. Pierce, we looked at these with alkenes. Does this work with alkynes? The answer to that is yes. And we are going to look at that in our next screencast.